Hello everyone, myself Rupam Das, Assistant Professor of Asansol Engineering College in Electronics and Communication Engineering Department. Name of the subject is Signals and Systems. Learning outcomes are at the end of the session, you will be able to understand LTI system and some of the basic properties of LTI system. Contents are LTI system, causality property, stability property, and unit step response of LTI system. Reference books are: first book is Signals and System by Anand Kumar, second book is Signals and System by Turun Kumar Rawat, third book is Signals and System by Ramesh Babu, and fourth book is Signals and System by Nagor Kani. Now, introduction to LTI system. Both the continuous time and discrete time system have several basic properties. Out of these several basic properties of system, two properties named linearity and time invariance plays a very vital role in the analysis of signals and system. If a system has both the linearity and time invariance properties, then the system is known as linear time invariance proper system. Next is definition of convolution of continuous time signal. The convolution of two continuous time signal x1t and x2t is defined as x3t, that is equal to minus integration minus infinity to plus infinity x1 lambda x2t minus lambda d lambda, where x3t is the signal obtained by convolving x1t and x2t, and lambda is the dummy variable used for integration. The convolution relation of equation can be symbolically expressed as x3t is equal to x1t convolution of x2t. Here star indicates the convolution operation. Response of LTI continuous time system using convolution. In an LTI convolution time continuous time system, the response yt of the system for an arbitrary input xt is given by convolution of input xt with impulse response ht of system, and it is expressed as yt is equal to xt convolution of ht, that is equal to minus infinity to plus infinity x lambda h of t minus lambda d lambda, where the symbol star indicates the convolution operation. Next, causality for LTI system. This property says that the output of causal system depends only on the present and past values of the input of the system. The continuous time LTI system is called causal system if its impulse response ht is 0 for t lesser than 0. For a causal continuous time LTI system, the convolution integral is given as yt equal to xt convolution of ht equal to tau is equal to minus infinity to t x of tau h of t minus tau d tau, that is equal to xt convolution of ht equal to tau is equal to 0 to infinity h of tau x of t minus tau d tau. A discrete time LTI system is known as causal system if its impulse response Hn is 0 for n lesser than 0. For causal discrete time LTI system, convolution sum is given as yn equal to xn convolution of Hn equal to k equal to minus infinity to n summation xk x of hn minus k, that is equal to hn convolution of xn, that is equal to summation of k is equal to 0 to infinity xk h of n minus k. Next is stability for LTI system. A stable system is a system which produces bounded output for bounded input. Now let us determine the condition under which LTI system are called stable. Condition of stability for continuous time LTI system. Let us consider an input xt that is bounded in magnitude. So mod value of xt lesser than m for all values of t. Now we apply this input to an continuous time LTI system with unit impulse response ht. Output of this LTI system is determined by convolution integral, and it is given by yt equal to integration tau is equal to minus infinity to plus infinity h of tau x of t minus tau d tau. Magnitude of output yt is given as mod value of yt equal to mod value of integration tau is equal to minus infinity to plus infinity h of tau x of t minus tau d tau, that is equal to integration tau is equal to minus infinity to plus infinity h of tau x of t minus tau d tau. Substituting the value mod value of x of t minus tau lesser than m for all the values of tau and t, we obtain mod value of yt that is lesser than equal to integration tau is equal to minus infinity to plus infinity mod value of h tau into m into d tau lesser than equal to integration tau is equal to minus infinity to plus infinity mod value of h tau into d tau for all values of t. Now from the equation we can conclude that if the impulse response ht is absolutely integrable, then output of continuous time LTI system is bounded in magnitude, and thus the system is bounded input bounded output stable. A sufficient and necessary condition for stability of a continuous time LTI system is given as stability capital S equal to tau is equal to minus infinity to plus infinity mod value of ht d tau lesser than infinity. Similarly, we can obtain the necessary and sufficient condition for stability for discrete time LTI system. Consider an input xn that is bounded in magnitude. So mod value of xn that is lesser than m for all values of n. Now let us apply this input a discrete time LTI system with unit impulse response hn. The output of discrete time LTI system is found to be convolution sum, and it is given as yn equal to summation of k is equal to minus infinity to plus infinity x hk x of n minus k. Also, a magnitude of yn is given as mod value of yn that is equal to mod value of k equal to minus infinity to plus infinity hk x of n minus k, that is equal to summation of k is equal to minus infinity to plus infinity hk mod value of x n minus k. Substituting the value of mod of x of n minus k lesser than m for all the values of k and n, we obtain mod value of yn less than equal to summation of k equal to minus infinity to plus infinity x hk into m, mod value of yn less than equal to m summation of k is equal to minus infinity to plus infinity hk for all the values of k. Now from equation we can conclude that if the impulse response hn is absolutely summable, then the output of discrete time LTI system is bounded in magnitude, and therefore the system is bounded input bounded output stable. A necessary and sufficient condition for stability of a discrete time LTI system will be expressed as capital S equal to k equal to minus infinity to plus infinity mod value of hk lesser than infinity. Now if the system is also causal, then the output is bounded if and only if summation of k equal to 0 to infinity hk is bounded. In other words, stability is equal to k is equal to 0 to infinity mod value of hk lesser than infinity. Next is unit step response of a LTI system. The unit step response is the output of LTI system for input is equal to unit step function sequence. The unit step response of continuous time LTI system is found to be convolution integral of ut with unit impulse response ht, and it is expressed as gt is equal to ut convolution of ht, that is equal to ht convolution of ut, according to commutative property. Therefore, unit step response ht may be viewed as a response to the input ht of a continuous time LTI system with unit impulse response ut. The unit step response of discrete time LTI system is found by convolution sum of un with unit impulse response hn, and is expressed as gn is equal to un convolution of hn, that is equal to hn convolution of un. So these are the pictorial representation of unit step response of a LTI system, where xt is the input, yt is the output, and for discrete domain xn is the input and yn is the output. Now next, depending on this definition, we are going to see check whether the following system is bounded stable or not. So first question is yn is equal to a into x square n. So first of all, we are going to write xn equal to del n, yn is equal to hn. So according to impulse response, it is given by hn is equal to a into del square. We are putting the value of n over here. So first of all, whenever n equal to 0, so we can write h0, that is equal to a into del square 0, that is equal to a. And whenever n is equal to 1, so h is equal to h into 1, so that is coming a into del square 1, that is 0. So in general, we can write hn equal to a for n equal to 0, and its value is equal to 0 for n not equal to 0. So, and necessary and sufficient condition for bounded input, bounded output stability, and it can be expressed as summation of k is equal to 0 to infinity mod value of hk lesser than infinity. So we can write summation of k is equal to 0 to infinity mod value of hk, that is h0 h1 h2 plus dot 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 hk, that is equal to mod value of a. Therefore, we can conclude that the given system is bounded input, bounded output stable only if a lesser than infinity. Another question we are having, that is yn is equal to a into xn plus b. Here xn is equal to del n, yn is equal to hn. So the impulse response is hn, that is equal to a into del n plus b. First of all, we are going to put n equal to 0. So h0, that is equal to a into del 0 plus b, that is a plus b. And n equal to 1, so h of 1, that is a into del 1 plus b, that is b. So h1 is equal to h2, that is equal to hk, that is equal to b. So we can write hn is equal to a plus b when n equal to 0, and its value is equal to b for n not equal to 0. So the necessary and sufficient condition for bounded input, bounded output stability can be expressed as summation of k equal to 0 to infinity mod value of hk, that is lesser than infinity. So therefore, summation of k is equal to 0 to infinity mod value of hk, that is equal to h0 plus h1 plus h2 plus dot 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 hk, or summation of k is equal to 0 to infinity hk, that is equal to a plus b plus b plus b dot 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 up to infinity. So from the expression, it is obvious that the series never converge since the ratio between the successive term is 1. Therefore, the given system is bounded input, bounded output, unstable. Another question we are having, that is yn is equal to e to the power minus xn. So here in this case, xn equal to del n and yn equal to hn. So therefore, impulse response is hn equal to e to the power minus of del n. We are putting the various values of one for n equal to 0, another for n equal to 1. When n equal to 0, so h0, that is equal to e to the power minus del 0, that is equal to e to the power minus 1. When n equal to 1, so h of 1, that is e to the power minus del of 1, that is e to the power 0, that is equal to 1. So we can write hn, that is equal to e to the power minus 1 when n equal to 0, and its value is 1 for n not equal to 0. So the necessary and sufficient conditions for bounded input, bounded output stability is expressed as summation of k is equal to 0 to infinity mod value of hk lesser than infinity. So therefore, we can write summation of k is equal to 0 to infinity h of k. We can expand the series, so it is coming h0 h1 h2 plus dot dot up to hk. So depending on that, it is coming e to the power minus 1 plus 1 plus 1 plus 1 up to infinity. So therefore from the above equation it is clear that the system never converge, therefore it is bounded input bounded output unstable system. Next we are going to see interconnection of continuous time system. Smaller continuous time system may be interconnected from large system. Two possible basic ways to interconnection of one is cascade connection, another one is parallel connection. This is the block diagram of cascade, this is the block diagram of parallel connection. Now in case of cascade connection of continuous time system, two cascade connection uh, time system with impulse response h1t and h2t can be replaced by a single equivalent continuous time system whose impulse response is given by convolution of individual impulse response. So we can write down whenever xt is the input, after passing the system it is coming y1t, then it is passing through h2 t, it is generate the final output by t. Instead of doing this we can write down h1t convolution of h2t, then passing the input signal, and finally we get the output by t. And in case of parallel connection of continuous time system, simply we are applying ht, this is the parallel connection. Instead of doing the output, taking the output from the system, we can and make the addition of the impulse response, that is h1t and h2t, then apply the system input, and finally we got the response yt at the output. So this is the parallel connection of continuous time system. So in this way we can get the output. Next is discrete or linear convolution. First of all, formula: the discrete or linear convolution of a two discrete time sequence x1n and x2n, it is given as x3n, that is equal to summation of m equal to minus infinitive to plus infinitive x1m and x2n minus m, or x3n, that is equal to m equal to minus infinitive to plus infinitive x2m x1n minus m, where x3n is the sequence obtained by convolving x1n and x2n. M is the dummy variable. If the sequence x1n has n1 sample, x2n has n2 samples, so the x3n, that is the output, will be the finite duration of the sequence consisting of n1 plus n2 minus 1 samples. The convolution result in a non-periodic sequence, since the convolution is also known as aperiodic convolution. The convolution relation from the above equation symbolically can be expressed as x3n is equal to x1n convolution of x2n, that is equal to x2n convolution of x1n. The symbol star indicates the convolution operation. Next, these are, depending on that you are having some properties: commutative, associative and distributive property. Commutative property indicates x1n convolution of x2n, that is x2n convolution of x1n. Then associative property, x1n convolution of x2n convolution of x3n, that is coming x1n convolution of x2n convolution of x3n. Distributive property indicates that x1n convolution multiplied by x2n plus of x3n, so it is coming x1n convolution of x2n plus x1n convolution of x3n. So these are the properties of convolution. So next is interconnection of discrete domain system. This particular system is again divided into two categories. First one is the cascade connection, second one is parallel connection. Previously in continuous domain we have seen the same thing, only difference is that in previous the whole thing is in terms of a t, but here in this case, as it is the name discrete time system, so whole thing is denoted in terms of a n. So we can solve it by one. So in case of cascade connection discrete time system, we have to apply the input, then it passing through this, it generates the output y1 n, then again it's passing through the output, it generates the output yn. Instead of doing this, we can make a convolution of this to impulse response, so it is coming h1n convolution of x2n, and then again apply the input, and finally you got the response from this particular section. This is one way. Another way for parallel connection discrete time system is, this is the parallel connection. So instead of doing this, you have to add these two sequence h1n and h2n, then apply the input, and finally you got the response from yn. So this, in this way you can obtain the result. So depending on that, you are having one mathematical question. Determine the impulse response of a cascade 2 LTI system having the impulse response. One is h1n, that is half to the power n of un. second one is h to n, that is equal to 1 by 4 to the power n into un. So according to the convolution property, we can write hn is that is equal to h1n convolution of h to n. We can expand it. So it is coming summation of m equal to minus infinity to plus infinity h1n h to n minus m, where m is the dummy variable. So we can write down this expression like this: keep hn that is equal to m equal to 0 to in n h1n h to n minus m. We just put down the value of h1n and h2m like in this manner: half to the power m and 1 by 4 to the power n minus m. It is unit step function is there, so that's why the limit is changing from 0 to up to n. Then we can expand the series: half to the power m, 1 by 4 to the power n, 1 by 4 to the power minus m, 1 by 4 to the power n, it's coming outside. Then after solution it is coming 1 by 4 to the power m into 4 to the power m. Then on after simplification it is coming 1 by 4 to the power m summation of m equal to 0 to n from 2 to the power m. So we can use this particular formula for geometric series. Whenever summation of n equal to 0 to n, that is c to the power n, so it can be written c to the power n plus 1 minus 1 divided by c minus 1. So we just put down the value over here: 2 to the power n plus 1 minus 1 divided by 2 minus 1. By using this particular formula, we can get the result 1 by 4 to the power n, 2 to the power n plus 1 minus 1 whole into un for all the values of n. So up to this, I'm concluding today's session. Thank you all.